Let the chemistry excitement continue. And the mystery, really. So as we go into further understanding of the electron, its behavior, we get to the phenomenon that was observed when running electrical current through gases, the observation of emission spectra. Okay, so like the light that was emitted off of atoms when they were excited and molecules gave out specific spectra. So when you excited this light source, rather than seeing the full spectrum that white light gives off, and white light, when we talk about white light, it's really when you heat up something, heat it up to a point where it produces light. So when you think of like a filament, so a traditional light bulb that has like the little filament in it, the reason why it gives off white light is we're taking this piece of metal and we're heating it up to a point where it gives light. And that is related to it getting really, really hot. So a hot body spectrum is what it's referred to as. But when you run electrical current through specific elements or gases of elements, you do not see, it does not behave the same way. This isn't heating something up to get a full spectrum. You actually get just light at specific wavelengths, what we call a line spectrum, giving discrete wavelengths observed for specific elements. And so what this led Niels Bohr to adopt Planck's assumption and explain the phenomenon in a couple ways. One, electrons in an atom can only occupy certain orbits corresponding to certain energies. The idea that the electron, rather than being able to be wherever around the nucleus, is in fixed locations around the nucleus. Now, Niels Bohr held to the idea of orbits. We'll get to how that changed slightly, but really this idea that the electron is bound in certain regions because of these bands of light that we saw when excited, when the electrons get excited. Second, electrons in permitted orbits have specific allowed energies. These energies will not be radiated from the atom, meaning the electron can be excited, move up to higher energy levels, can come back down, but can't go into any location. There's defined locations where it can be. And then third, energy is only absorbed or emitted in such a way as to move an electron from one allowed energy state to another. The energy is defined by E equals Planck's constant times frequency. So what does that mean? How does that come in? So when electrons absorb energy, they absorb specific amounts of energy. They can't absorb all of it to go to go any certain distance away from the nucleus. They can absorb specific amounts to go up to certain energy levels. So how we apply this, or how we can now apply it, is when we think about the energy absorbed or emitted from the process of an electron being promoted or demoted in an energy level can be calculated according to this equation, where you have the change in energy is equal to Rydberg's constant, so just another constant, and notice the units of that, 2.18 times 10 to the negative 18th joules, and then the initial energy level and the final energy level that the electron moves between. So potentially, if the energy level that the electron, so let's say the electron starts in the ground state at 1, and then it absorbs energy to jump up to the third energy level. Well, then you would have 1/9 minus 1. Okay, so then you have that difference and do the math, and it gives you the energy associated with that change or that movement of the electron, showing how much energy the electron absorbed. Or let's say the reverse. So let's say it's started up at the third energy level and it ended at the ground state. So it went from, so the n final column would be 1 minus 1/9. Well, you're going to have a much larger number, and therefore the energy will be negative, giving off energy in the process, and that's typically in the form of a photon, the light that you see in the spectrum. So where does this take us next? This takes us to the idea that light can have both material properties, but matter should also exhibit wave properties. So it's this balance, and pairing the two relationships together. The wave nature and the particle nature of matter blends the two, where we have wavelength equals Planck's constant over mass times frequency. Another aspect of this behavior, this particle nature of electrons, is the Heisenberg uncertainty principle. So Heisenberg showed that more precisely, so if we can determine the momentum of a particle, specifically electrons, the less we can know about where it is positioned around the nucleus. So that's this relationship here defined in this equation. And the Heisenberg uncertainty principle is something that, if you go on to take a lot of chemistry in college, your physical chemistry course, where you'll study the calculus of chemistry, how we know the behavior of the electron in a far more detailed way. You explore the Heisenberg uncertainty principle and do derivatives based around it. So some really cool calculus around understanding the electron. But in many cases, our uncertainty of the whereabouts of an electron is greater than the size of the atom itself. So if we know the momentum, then literally our certainty in where the electron is so low that the atom itself is too small to define where the electron is. So can't know both at any one time, which, I just ask for you to just kind of hold that loosely in your understanding, because I get it that for some of you that just doesn't sit well with you, but know that you don't have to have a firm grasp on this idea of the uncertainty principle. It's just kind of be aware of that occurs, and so that's going to lead to what we look at next when it comes to orbitals and the quantum mechanics of the electron.